I think we're on track to be where we need to be. Okay, oh, that's part 4. Was that what the, oh yeah, okay, so this is related to part 4. So in part 4, the slide started out like this. So we're solving equilibrium constant expressions, and you need to know, in order to solve it, what you guys did was you knew the initial concentrations of everything and equilibrium concentration of everything. Well, you can also solve them if you know the initial concentrations of everything and the value for the equilibrium constant, Kc. It's a little hairier, but that's what we're going to do now in part 5, that other type of problem. In this case, you're going to see, hopefully you saw the ICE table. We're definitely going to use the ICE table approach. I just think it helps keep us organized. So let's take a look at what that looks like. So basically, in our ICE table, we have initial concentration set up. Our next row is going to be the change in concentration in terms of some variable. We're going to make that x. We're going to use stoichiometry to know how much x goes for each species. Okay, we're going to call that the change, and then we're going to actually take the initial, apply the change, and get the equilibrium concentrations. The problem with this sort of problem is that you're going to end up with the equilibrium concentrations are going to have the variable x in them, and it's going to drive you nuts. But you have to somehow, you're going to have x, one variable is equal to the Kc, which you were given. And so you're going to have to solve for x, okay? So it's got some math part things going on. Once you solve for x, I don't know if you follow what I've been trying to describe, it's easier to show you, but once you know what x is, then you can go ahead and look at your ICE table and say, oh, well then I know I can apply my change and get my equilibrium concentrations. All right, so let's do it. So for instance, we have this H2 and F2 go to form HF, okay? We could write and your Kc is given. Your initial concentrations of everything is given. Now notice in this case, looks like we have 2 moles of H2, 4 moles of F2. So we only have reactants. One of the tricks to working these sort of problems is to know which way it's going to go. But does this make sense? It has to go towards products because there are no products. Okay? So we could come up with the equilibrium constant expression. Of course, it would look like this. It's the molar concentration, always the products in the numerator and the reactants in the denominator, their molar concentrations raised to their stoichiometric coefficients. So that's what we're going to plug into from the equilibrium concentrations. Remember, I kind of said you could go with subscript e's there. Those are equilibrium concentrations. All right. So we had a little bit of work to do on the front end because we were given moles and we were given the volume of the container. These are all in their gaseous state. So we could knock out molarity of H2 and it would look like this. We had 2 moles of H2 in a 2-liter container. I can do that math. So you're looking at 1.00 moles per liter for your H2. The F2, we said there was 4 moles of F2 in the same container, which is a volume of 2.00 liters. So your molarity must have been 2.00 molar F2. What was the molarity of your HF? 0, right. A real common, and maybe that's why I kind of make us do this, a real common mistake is that students will want to, for the initial, they'll want to plug in moles. It's not moles for the initial, it's molarity. So don't fall into that trap. So instead of little subscripts e's, we have little subscript zeros, which mean initial. So that's going to go in our first row in our ICE table. So in 4 slides from now, if you want to look at 4 slides, you'll see the ICE table. And I just moved it forward because I'm a fan. So what we do with the ICE table is we have columns for all the species. So I've seen sometimes they put the products first, sometimes put the reactants first, but here you can see I have 2 reactants, H2 and F2. I have 1 product, HF, so those are my columns. And then I'm going to have 3 rows. My first row is going to be initial. My second row is going to be change, and then I can draw a line here. I'm going to take my initial and apply my change to get my equilibrium concentration. So on the previous slide, we knocked out the initial molarity of H2 is 1.00, initial molarity of F2 2.00, initial molarity of HF, you told me nothing. Now, this is where we need to use the stoichiometry of the equilibrium to come up with the change in terms of some value x. I don't think I say it on any of my slides, but what works well is if you find something that has a coefficient of 1 and make that x, that makes life easier. And so if that's a change of 1x, that's going to be a change of 2x. That a coefficient of 3 would be 3x, etc. So our change, we say it has to go to the product side. So we're going to have a negative 1x for H2, a negative 1x for F2, and a plus 2x for HF, just from the stoichiometry. And again, it doesn't have it on these ice tables, but I really think of an ice table like this, where this is my line, and I have a plus there. So my equilibrium concentrations, like I told you before, it's going to drive you a little nuts because it won't be a number. It'll be your equilibrium concentrations in terms of one variable. What you're going to, what's that?
Yeah, so the molarity, that's just already implied because it's up on top.
Yep, the molarity. Oh, I see what you mean. Yeah, I didn't put M's here. Yeah, but I do sometimes put them here. But yeah, I guess you wouldn't have to if the column says M. Yep. So you take the initial, you apply the change. So at equilibrium, you're looking at H2 being a 1.0 minus X. At equilibrium, F2, 2.00 minus X. And at equilibrium, your HF is going to be 2x. Okay. So what your slides do now, and we're going to get the same relative amounts. So this slide's just kind of, this is without an ice table. So if we let X be the change in mole, if we let X be the the molarity of H2 that react, moles per liter that react, then that will also be the moles per liter of F2 that react because they have the same stoichiometric coefficient. And then the 2x will be the amount of HF form. That's just your change. Okay. Let's see. So this right here, this says be careful when working these sort of problems. And actually this is where, if I were to say two units kind of piggyback from each other, it would be unit 3 and unit 4. What we cover here, conquer here in unit 3 is going to carry into unit 4 when we talk about acids and bases. All this says is when you're doing, if you're doing an ice table, when you're doing your change, make sure you know whether it's adding or subtracting. And this goes back to, remember when we took, and we're going to do an example here today, when you do a snapshot, your QC, to see if it's larger than or smaller than your KC, to know which direction it's going to go. In this case, it was obvious we had no HF, so that's going to be a plus 2x, and our two reactants are going to be a minus 1x. Okay. Oh, and I added this. Yeah. Just this last minute. Yes. I'm going to read to the English theater to see what you guys don't know. I don't even know either. Steve Earle. That's what it's all about. Anyway, so yes, you need to know which direction it's going to go, so whether you're adding or subtracting. It's a really common mistake. Okay, so based upon, this is finishing up the ice table. See, I'll let you fill that in. This is finishing up the ice table. This is that last row that I had an ice table. It simply said then, if we calculated earlier the molarity of our H2 and the molarity of our F2, okay, then we know at equilibrium it's going to be for H2, it's 1.00 minus X. For F2, 2.00 minus X. For HF, it didn't have any. We add 2x, we get 2x at equilibrium. This is the same as that third row. I really like the ice tables. I don't have to think so hard. Okay. So what you're going to see on the next slide then, before I go there, is basically we're going to take these quantities and we're going to substitute these three quantities back into our equilibrium constant expression. We have to be careful, because when we substitute them in, remember we have to, in the case of what, the HF, we're going to have to square that term, right? Okay, so there's the table I did. Okay, here we go. Here's our equilibrium constant expression. Again, this is an example where we're given the initial concentrations of everything and the value for K. And we're supposed to find the equilibrium concentrations of everything. We're working on it. So this then is what the substitution looks like. So the numerator, you have the quantity 2x raised to the second power. In the denominator, you have the quantity 1.00 minus x times the quantity 2.00 minus x. Okay. So I always wonder each semester how to do this, and I think this is how I'll do this semester. I hope this makes sense. So this step right here, this step, for exam, stop here. Stop at this step. And I'm going to say for homework, and I'll do HW for homework. For HW, solve for X. Hope that makes sense. Because we're going to go ahead and solve it for X. And there's a number of different ways you can do it. But if you get this far, then you're done. Okay? All right. But you have to drag yourself through it. And on my answer keys, you'll see kind of where I solved it. So it's not always great. Here in a minute, you're going to see that since this is a polynomial, but it's brought just to the second power, I'm not a math teacher, you're going to see that we can actually use the quadratic equation, if you remember that ugly looking beast, okay? But to turn it, to flatten it out, we have to, and people learn it different ways, we basically have to take those two amounts and multiply them through by each other. So to me, I take this times this, and this times this, and then I take this, and I add it together. Anyway, so if I take this, the 1.00 times the 2.00, I get, of course, 2.00. If I take my, well, I guess I'll do this next. I think, it's ugly. So now for my x term, I'm going to have, what, a negative 2x here, and I'm going to have negative 1x here. Sorry about that. So negative 2 plus a negative 1, that would give me a negative 3.00x. And then I'm going to take my last ones, and a negative x times a negative x is a positive x squared. So this quantity is this quantity. Okay. So if I were to rewrite this, oh, maybe I'll do it this way. There's no line there. I've got to rewrite this, and let me go ahead and expand that out. What is 2x quantity squared? I have to take my square in for the 2 and my square in for the x. So that's actually 4x squared. So this thing ends up being 4x squared over 2 minus 3.0x plus x squared. That's all equal to your 115. Now, I usually think of 115 over 1. I know this is really ugly, I'm sorry. So I have this quantity is equal to this quantity. And so to flatten it out, what I usually do then is, I call it cross multiply. I'm going to take 115 times the stuff in the denominator is equal to 4x squared times my 1. So I'm flattening it out. So what I just said is I can 115 times my 2.00 minus 3.00x plus x squared is equal to 4x squared. Cool, golly galolly. Then I'm going to take my 115 through this quantity. So 115 times 2, what is that, 230? I'm going to if it's okay with you, just disregard my decimals. 230 minus, and I have to take 115 times 3.00x. 15 times 3. I get 345x plus 115x squared is equal to 4x squared. What's that 4x squared there? I'm trying to get it into a format where I have 0 on my right side of my equation. So I'm almost there. So now I'm going to take this 4x squared in here, find the term it matches with, and so I'm going to have to subtract 4x squared from both sides to get 0 over there. So I get the standard form start with the x squared first.
Yeah.
Oh, thank you.
It doesn't decrease in power.
Thank you very much. Okay, so I'm going to take, if I add negative 4x squared to both sides, I get 111x squared minus 345x plus 230 is equal to 0. So, okay. Anyway, that's what we call standard form. Any questions so far? Because I didn't show any of that, because I just go to this. But this is where that came from. Okay? I'm going to show, well, you have options. Then I don't have time to show you all the options. But if you get it that far, then you're ready to use the quadratic equation. But now, wait a minute. Did I tell you that you need to solve it on a test? Yeah. So honestly, I think I'm saying this right. There are online, and maybe even that handy-dandy calculator you can't use on your test, there are little ways to go ahead and plug this in to get a value for x. I think when I did the problems for your answer keys, I used Wolfram and Alpha. You can just go out there and say solve polynomial and polynomial solver. Or I brought in this today. This can do it. You don't have to get it in the standard form. Okay, so let's just say you got it in the standard form. Since it's just the highest it's got is the square, we can use the quadratic equation. Yep, and like Jacob said, here's the form. So in a minute when you see the quadratic equation, the value associated with x squared is going to be a, the value associated with x is going to be b, the value of no x is c. So there's the quadratic, and you plug those values in. Now you'll end up getting 2 solutions, and the 2 solutions come from right here. And if you've done this very much, you're like, oh, I hate the quadratic equation. Some people love it. But you will get 2 solutions because in one case, you're going to add the square root of b squared minus 4ac. In the second solution, you're going to subtract that quantity, b squared minus 4ac. All right. So here's, so you get 2 solutions. You might be like, well, Mrs. Snipes, if I get 2 solutions, what the heck? Well, one of those solutions won't make sense because x will be larger than what you started with. And if you remember your ice table, you're subtracting that, and so you're subtracting x from the initial concentration of H2 and F2. So it can't be larger. You can't subtract more than you have. So let's take a look at what this looks like. You'll get 2 solutions. This is what, of course, your 111 will be A, your negative 345 will be B, your C will be 230. It's kind of fun, I guess, if it works. Okay. So this is what it's going to look like with your quantities plugged in. Again, your 2 solutions come from, you're adding this quantity and subtracting this quantity. So putting it in the quadratic equation, these are our 2 possibilities. And if you look back at your ice table, which one of these does not make sense? The 2.14 does not make sense. Yep. because we only started out with, was it 1.00 and 2.00, so neither one of those will work. But our other one will. And we're almost done. Because now, if you use the ice table, or if you didn't use the ice table, you still have to show your logic in getting there. Now we're ready to go back to those equilibrium concentrations that had a value for X. Plug in 0.986, and we have our equilibrium concentrations. Okay, so for instance, the molar concentration of H2 at equilibrium is 1.00 minus 0.968, which is, now the problem here, remember we learned back in Chem 1, is since we're subtracting here, we can only allow with the fewest decimals. So I only have 2 decimals in my molarity, and I have like 3 decimals in my X. So I have to go with 2 decimals, which feels weird. And I know OpenStax doesn't always follow the rules. So 0.03 moles per liter. For the molar concentration of F2 at equilibrium, we had initial was 2.00 minus X minus 0.968. That gives you a 1.03 moles per liter. And equilibrium, our HF is going to be 2 times 0.986. And the reason I'm giving 4 sig figs here is because I'm kind of going with, instead of 2 is exact, and so I can think of this, in addition to 2, I can think of this as basically adding it to itself. So I have 2 of these terms added together, which puts me back at decimals, so I have 3 decimals. Now, this is one, there are a few problems in chemistry, and this is one of them, that you can actually check your answer. How could you check your answer? Okay. Average atomic weight is another one to check out. Look at the periodic table. You just take these values and you plug them into your equilibrium constant expression and see if you get 115. Yep. And if you don't, something went wrong. Something went horribly wrong. Okay, so you can check your answers. All right, any questions about that one? So we're going to do another one. Takes it up a notch. Different equilibrium, everything's in a gaseous state, which makes life easy. Everything, you're talking about stoichiometric coefficients of 1 across the board. This is another example where your equilibrium constant was given, the 0.190, and they don't give us moles, now they give us in grams. They don't give us molarity, they don't give us moles, they don't even, so we have to, anyway, we're going to have to take these grams, they give us the volume of the container though. So basically, we're going to have to take those masses, convert them to moles, and then divide by the volume to get molarity. All right. So I have a couple questions here though. So we're gonna come up with the initial molar concentrations of the reactants and the 2 products using those masses and the volume. And then we're actually going to first say whether it's in an equilibrium. How are we going to know if we're going to go to the left or the right to the reactants and the products? Yep. We're gonna make a QC and compare the QC to the KC. Yep. We're gonna come up with that snapshot, our reaction quotient, and compare it to our KC. And that's important, like I said a few slides ago, because you need to know whether you're going to be subtracting X or adding X in your change flow. Once we've done that, we're going to go ahead and I'm going to use the ice table approach, and we're going to go ahead and knock out the equilibrium concentrations. All right. So, like I said, and I guess here I said it, but I'm saying the same thing I added last night, that you need to know whether you're going from to form products, so your products are building, your reactants are getting less, so these will be negative, that will be positive, or whether your products are going back to form reactants. So in that case, your products are getting less and your reactants are getting larger. Gotta know that. So you guys could knock out the equilibrium constant expression. It would look like this. Everything's in their gaseous state. Remember, if it's in solid liquid state, it does not show up. If it's in aqueous solution, water doesn't show up. So the QC is going to take the reaction quotient expression takes the same form. The QC is not necessarily at equilibrium. That's why I call it a snapshot. So the QC will also be the molar concentration of CO times the molar concentration of Br2. Those are the products raised to the first power. That's their stoichiometric coefficient, divided by the molar concentration of the reactant, the CO Br2, also raised to the first power, because that's its stoichiometric coefficient. Okay, and then I was like, oh man. So when I come up with, I'm going to have to use grams to get to molarity. I don't show knocking out the molar masses of these things, so just go with it. You would have to, on a test, knock out the molar masses of everything, but for the molar concentration of CO, they gave a mass of 33.4 grams. It's confined to 1.50 liters. And if you were to go to the periodic table and look up what CO is and what carbon is, what oxygen is, you would get 28.01 grams per mole. But notice that I'm using the flipped version of the molar mass. So my grams of CO will cancel. I'll be left with units of moles per liter. 3 sig figs. So the initial concentration of the CO is 0.795 moles per liter, or molar. With the Br2, again, I would come up with the molar mass, take 2 times what it weighs, which it weighs a lot, and use that as my second term. My first term was the mass of the Br2, which was 70.7 grams, also in the container, which is 1.50 liters. I multiply that by the flipped version of the molar mass, 1 mole over 159.80 grams. So our grams cancel, we're left with units of moles per liter. 3 sig figs again, so the initial molar concentration of the Br2 is 0.295 moles per liter. And then last but not least, the original problem said we had a whopping 128 grams of COBr2. So I have 128 grams. It's also, again, the volume of the container containing all 3 gases is 1.50 liters. The next term is the flipped version of the molar mass of COBr2. So 1 mole over 187.81 grams. So again, we use the periodic table, take 1C plus 1O plus 2 Br2s. Get 187.81 grams per mole. Grams cancel. We're left with units of moles per liter. 3 sig figs. And you're looking at 0.454 molar or moles per liter. I know I did these in DMAC yesterday afternoon while I was waiting to leave the conference. I didn't do it last night. Okay, so this is going to be, this initial concentration, that's going to be our first row. So here we go. No, it's not going to be our first row. Yeah, well, it will be our first row, but remember our first step is to do the snapshot. We need to do the QC first. Okay, so here's what our QC would look like. Again, everything raised to the first power because stoichiometric coefficients are 1. So we have the 0.795 times 0.295 in the numerator divided by 0.454 in the denominator. So you're looking at a reaction quotient of 0.517. Was that greater than or less than? It's greater than, so it's too big. So which way is it going to go? Yes. Toward the reactants. It's too big. Yep. So we need to take some of the products and convert them into reactants. Yep. Reactants. So it's going to be X's across the board because there's significant coefficients of 1. So what do you think? The X with the product, will that be positive or negative? Negative X. Yep. And the other two will be positive X. Exactly. Yep. So I would set up an ice table. This is actually 3 slides from here. It should look like this, where we have, we're setting up our columns. So our columns, we have the 2 reactants in the product. And then of course we're going to have 3 rows, initial, change, and at equilibrium. The initials we knocked out. We had the 0.795 for the molar concentration of CO, the 0.295 for the molar concentration of Br2, 0.454 molar concentration of COBr2. You told me that we're going to go with, oh man. Oh, okay, thanks. Yeah, so it's turned around. So yeah, the products, you say we're going with negative X's. So, yep, so negative X there, the reactant, it's going to build. Positive X. So at equilibrium, again, I usually, for my ice tables, I like to do a line here after the first 2 rows, and I put a plus here, just to remind myself what's going on. Now, when I got the quantity into standard form last time, I had what, a value of like 1.00 minus X or 2.00 minus X. Now this is looking a little uglier even still. So what we got to do next is, and actually my next slide is just kind of cut through. We let X be equal to the moles per liter of CO that react. Then it will also be equal to the amount of Br2 that reacts. And it will be equal to the amount of COBr2 that's formed. Then you guys told me that my products, not just my product, my products actually will be decreasing. So I'm going to apply negative X. And my reactants will be increasing, will be positive X. Did I put all that stuff? Ice table. Ready to substitute in. So here's our equilibrium constant expression. We substitute in quantities. It looks like this. Go get a cup of coffee. Wait a minute. So what did I put a few slides ago over here? This is where you stop for the test. Yep, this is where you stop for the test. But over right here I said that you have to keep going, and you get to keep going for homework. Yep. And I'm not going to pull us through getting into standard form, but it'll be a similar approach. Okay. Yeah, and it's a phrase you never forget. You have one equation, one unknown. You should be able to solve for X. If you wrangle it into standard form, this is what it's going to look like. So of course your A is 1, your B is 1.280, your C is 0.148. Ugh. I've actually worked with students that again, it seems so limited because it's polynomials that only are raised to the 2nd degree. So anyway, yep, you get two solutions for X. Let's see if one makes sense and one doesn't make sense. So X could either be 1.15 or it could be 0.129. Which one doesn't make sense? The top one doesn't make sense. And you know, I'm thinking it's always going to be that way. And I can't remember if sometimes you get a negative quantity. I'm not sure. And then that one would make sense. Yep. And we're going to have time here in a minute. We'll kind of do a little playing around with, if I don't want to mess with the quadratic equation, what are my options? If I have access to a calculator, if I have access to the internet, which you will for your homework. What the heck? Okay. So we're not quite done yet. We need to take that value for x and slap it in for x in our equilibrium concentrations. So for the CO, it would be 0.795 minus that 0.129. Only 3 decimals is what we're allowed. So we get, you can't make this up, 0.666 moles per liter. So for the equilibrium concentration of VR2, we take the initial, which was 0.295. From that we subtract, again, the x, 0.129, and we get a molar concentration of 0.166 moles per liter. And then for the COBR2, we need to add x. So for the COBR2, we have 0.454 plus 0.129, and we get 0.583 moles per liter. Now, isn't it fun that you can take those quantities and substitute them back into your equilibrium constant expression and make sure you're, I don't know, maybe it's just me, make sure you got it right. Or maybe you don't want to know. Sometimes I don't want to know. Like, ignorance is bliss. So, okay. So I know some of you guys have TIs. When I was playing with my TA, don't forget that if you've long lost your user manual, you can go on the internet for user manual. Now for my TI, I was playing around with it because it's been a while. But if I go to my math mode and then go down, I've got an option called Solver. And that will get you started. If I push enter for Solver, this one actually, though, is looking like it wants it in standard form because it gives my zeros equal to, so I'm not sure. You'll have to read your specific thing. But before I let you go, I do want to show you your options out there for on the internet. Oops. I mentioned Wolfram Alpha. They've got a lot of neat science things. I don't know if they're all science or, but if you just, let's see, what would I Google? What did I Google? Polynomial solver. Polynomial calculator online. Polynomial calculator online. And you can kind of see where I visited some of them because they're a different color. They're kind of purple instead of blue. But this is the, and some of them, you just, I don't know. This one, enter the expression, but it doesn't have an equal to. Oh, I didn't like that one. So you'll just have to play around with it to solve for x. But they're out there, and I think I might have pushed something out on Canvas. I meant to, or I did, or meant to. If you find one you really like, let me know. So, like, tell me in standard form what was that first one. So it was 111 x squared. Right? Oops. X squared minus, or was it plus?
Minus 345x.
Thank you. 345x plus 2 is equal to 0. Go, 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 go. Now remember, they're trying to teach you things, so they'll give you a lot of blada blada. Just be prepared for it. Final solutions. Well, I just want the number, people. Do you guys see it? Maybe I passed it. They don't give you the, oh, here it is at the top, maybe. X is equal to, yeah, there we go. All right, I'm feeling better. So for this one, you see at the top, is that what we can, I feel like I'm playing with it, okay. And for this one, to me, as long as you use parentheses and all that and you nest them correctly, you don't have to get it to standard form. So let's go back up. Give me the ugly one. Give me the one we just did. So what was in the numerator? Like the one we just did with the CO and the BRK.
You want this statement, please?
No, I want this ugly one here. This one, 0.07. Sorry, 0.79.
795 X. Or 795 minus X.
795 minus X. Notice I'm doing the brackets like 2. Do you know what I'm saying? What was the next quantity in the numerator?
0.295 minus X.
295 minus X. Excuse me. And then that's divided by what's in the bottom?
0.454 plus X.
And that's equal.
190.
Point what?
0.190.
0.190. Go, go, gadget, go. Let's thinking. All right. I think I'm like, this is my favorite one right now. Because at the top was the correct value for X, 0.12. 8, 7, 9. Yeah. Okay. So it's symbollab.com. It's a good one. It's a keeper for your homework. Because all of them are kind of strange, but okay. Yay. That's all I got. So that homework is due when we meet again on Friday.